Today we are going to learn about mastering KL divergence for AI optimization. We will explore how to calculate and apply KL divergence in AI models to enhance model performance and accuracy. By the end of this video, you'll have the skills to use KL divergence effectively in your AI projects.
Welcome to our session on mastering KL divergence for AI optimization. KL divergence, also known as Kullback-Leibler divergence, is a fundamental concept in information theory that measures the difference between two probability distributions. Developed by Solomon Kullback and Richard Leibler in 1951, it has become vital in various fields, particularly in AI and machine learning. Understanding KL divergence is crucial for comparing distributions, which can significantly impact model training and optimization. In this video, we'll explore its calculation, applications, and how it aids in refining AI models. Let's delve into the mathematics behind KL divergence. The formula is expressed as d_KL p vertical bar q equals px log px/qx, where p and q are two probability distributions. This formula computes the expected number of extra bits required to code samples from p using a code optimized for q. The summation runs over all possible events, and it's essential to note that KL divergence is not symmetric, meaning d_KL p vertical bar q, d_KL q vertical bar p. For continuous distributions, the summation changes to an integral. Understanding these nuances is vital as they influence how we interpret distribution differences in real-world applications. Measuring distribution differences is crucial in AI for evaluating model performance. KL divergence provides a quantitative measure of how one distribution diverges from a second, expected distribution. This is especially useful in scenarios where models are trained on different datasets or when updating models with new data. A lower KL divergence indicates that two distributions are similar, which usually correlates with better model performance and prediction accuracy. By understanding these differences, data scientists and engineers can make informed decisions in model selection and improve data-driven decision-making processes.
KL divergence is pivotal in optimizing AI models, particularly in the realm of loss functions. It is frequently used to measure the divergence between the predicted and actual probability distributions. By minimizing KL divergence, models can achieve more accurate predictions and efficient training processes. It also plays a role in regularization, helping prevent overfitting by maintaining a balance between fitting the training data and keeping the model complexity in check. Additionally, KL divergence aids in hyperparameter tuning, providing a metric for evaluating different configurations and guiding the optimization process.
Let's explore how KL divergence is applied in real-world machine learning models. In classification tasks, it serves as a useful measure for evaluating the similarity between predicted and true class distributions. In generative models like Variational Autoencoders, VAs, KL divergence is integral to the loss function, balancing the reconstruction error and the divergence between the learned latent distribution and the prior. In clustering, it aids in comparing cluster distributions, ensuring meaningful grouping of data points. These practical applications underscore its versatility and importance in crafting robust AI models. Implementing KL divergence in Python is straightforward with libraries like NumPy, SciPy, TensorFlow, and PyTorch. For discrete data, you can compute KL divergence using NumPy by calculating the sum of px log px/qx. For continuous data, SciPy provides integration functions to handle the integral form. In TensorFlow and PyTorch, KL divergence is often used in neural network training, with built-in functions simplifying its application. Let's walk through a simple example, calculating KL divergence between two discrete probability distributions using NumPy, highlighting the key steps and considerations in your code. While KL divergence is a powerful tool, it's not without pitfalls. One common issue is handling zero probabilities in distributions, which can lead to undefined calculations. To avoid this, smoothing techniques like Laplace smoothing can be applied. Numerical instability is another challenge, especially with very small probability values. Using log-sum-exp techniques can mitigate this. It's crucial to remember that KL divergence is asymmetric, which might affect interpretation if not carefully considered. Always ensure data is properly normalized to represent valid probability distributions, and choose distributions that appropriately model your data. In neural network training, KL divergence is often used as part of the loss function to measure the divergence between predicted outputs and target distributions. This case study focuses on its application in Variational Autoencoders, VAs, where it helps ensure the learned distribution aligns with the prior distribution. By penalizing divergence, KL divergence encourages the model to learn meaningful latent representations, enhancing the model's ability to generate realistic outputs. Through this case study, we'll see how KL divergence can drive better model performance and the insights gained from its application in neural networks.
When applying KL divergence in AI projects, it's essential to follow best practices to maximize its effectiveness. First, thoroughly understand your data and ensure it's properly normalized to represent valid probability distributions. Choose models that align with your data characteristics and project goals. Regularize your models using KL divergence to prevent overfitting and achieve a balance between accuracy and complexity. Continuously evaluate model performance, using KL divergence as a metric to guide improvements. Finally, adopt an iterative approach, refining your models based on insights gained from KL divergence analysis to achieve optimal results. In conclusion, mastering KL divergence is integral to enhancing AI models and optimizing their performance. By understanding its mathematical foundation and practical applications, you can leverage KL divergence to improve model accuracy and decision-making. We've explored its role in model evaluation, optimization, and training, highlighting its versatility across various AI applications. As AI continues to evolve, KL divergence will remain a crucial tool in developing sophisticated, data-driven models. Thank you for joining this session, and we hope you apply these insights to refine your AI projects successfully.